Okay, good morning friends. Today is lecture 3 of recursive robot dynamics. So far in last two classes we have studied about serial chain systems. From today we will start with parallel or closed loop systems, and the reference material will be available from this book, Dynamics of Tree Type Robotic Systems. Even though what I covered is little bit more fundamental, but the details will be available in this book. So, let us take a quick review of what we have done in the previous class. We have used RoboAnalyzer for inverse dynamics of one link arm, which we have derived in detail. Generalized inertia matrix for two link manipulator, also we have found out the components of it, each element of the generalized inertia matrix. We have seen inverse dynamics using RoboAnalyzer for KUKA robot. Forward dynamics and simulation, how the problem has to be formulated for single link, and then we have used RoboAnalyzer again for simulation, and then at the end some observation about using recursive dynamics. It basically means you should be using it for more number of links with more degrees of freedom. So, let us see what is a parallel manipulator. So, here this is an example of a parallel manipulator. This is the on the bottom what we have is called the Stewart platform. This is a real application where you have a truck chassis on the top of the top platform, and this is used as a truck simulator, very similar to the flight simulators which are used to train the pilots before they really go into the plane. So, in this case this is a truck cabin here in the front, the roads and the driver is sitting inside, and the different road conditions are inputted through the legs here, and the motion has been created. Let us see a small prototype which we have developed in our laboratory some years ago. So, these are the translatory legs here. This is the top moving platform and the bottom one is fixed. So, now it is showing a circular trajectory. Then it is writing on the whiteboard. So, you can try to guess what it is trying to write. M it has written, okay. I think the next one is appearing like E, and I am sure the last one you should be able to complete it. What is it? D. Okay. So, we stop. Okay. So, now before we go parallel manipulator which has many closed loops, let us talk about one closed loop which we all know is very solved the kinematic, that means I have solved theta 2, theta 3, and similarly for given angular rates for the first joint I have also calculated theta 2 dot, theta 3 dot, and similarly the acceleration. So, which means theta 1 double dot is a known quantity to me, and I 1 for a given system the inertia I know for the given length and mass properties. So, I 1 theta 1 double dot is equal to tau 1, that external which I have not indicated here. So, this will be here. So, tau 1 is here. So, tau 1 minus this minus, now these reactions are creating moments on this link about this mass center. So, all these equations are written about the mass center. So, tau 1 d 1 x 0 1 y, the component coming from here. Now, this can be better understood from the cross product formula. We know that this distance from here to here I have shown it is a d 1, but then from mass center to this edge it will be minus d 1 cross f 0 1. So, if you write in a component form d 1 cross minus d 1 cross f 0 1. So, this will be the term appearing. Then similarly for the other one, so this is from the reaction 0 1, and then if you write f 2 1 which is applying at distance r 1 from the mass center. So, r 1 cross f 2 1 will be looking like that. So, that is the rotational equation of motion for the first link. What about the translational motion? So, that is Newton's second law, m 1 c 1 x double dot. So, x if you assume in the this side. So, this is let us say x and this is your say y. So, m 1 c 1 x double dot is equal to all the forces acting on it. What are the forces acting on it? Are this 0 1 x and f 2 1 x. Just for you to note this thing, that f 2 1 x is nothing but f 1 2. F 1 2 is the force acting on the second body by the first body because of the Newton's third law. Now, the equation along y direction, m 1 c 1 y double dot is equal to f 0 1 y plus f 2 1 y. Now, these are three equations for one link. So, if we have 3 moving bodies, so there will be 3 into 3 9 equations. So, which I have written here 9 equation. So, 9 equations here. But how many unknowns are there? If you look at now f 0 1 has 2 components. So, it has a 2 unknowns, here are 2 unknowns. So, 2 to 4, this is 2 to 4. So, each body has 4. So, 4 into 3 12 and then tau 1 is the applied torque for the motion which we want to generate. So, total 13 unknowns which I have written it here. However, we know from the Newton's third law that f 2 1 is equal to f 1 2, which means 2 of the components are actually known. Similarly, here 2 of the components are actually known. So, 4 of them actually I know once I know the other one here. So, 4 I subtract from here from the Newton's third law. So, effectively I have 9 unknowns. So, 9 equations and 9 unknowns. So, each creates a determinate set of equations, and now I can determine set of equations which I can arrange in the following manner, which you will see in your book. Now, Ghosh Mallik, for example, theory of machines and mechanisms, which you might have studied. Now, this will create 9 by 9 matrix. So, first 3 corresponding to first link, the second 3 corresponding to the second link, and the last 3 corresponding to the third link, and corresponding unknowns are put in the columns. So, if I give this matrix a name A, which is 9 by 9, I write this vector as x 9 by 1, and the right hand side are my known quantities, because as I told you the kinematics is solved. So, I know all these acceleration values, the mass parameters are also known. So, I could find out this one. So, now it forms A x equal to B form. Using our linear algebra knowledge, I can solve x equal to A inverse B, but as I mentioned one of my earlier classes, that we do not explicitly invert A because of computational disadvantages to find explicit inversion. We decompose A as A into L into U, these are called LU decomposition using Gaussian elimination. And then u x I assume as a y vector. So, L y I solve L y equal to B using what is known as forward substitution, and then knowing y I calculate u x equal to y, which is called the backward substitution here. Okay. Now, one of the disadvantage you may find, for example, if I am interested with inverse dynamics, which means for the given motion how much is the torque to be applied, but you see along with the torque I am calculating other 8 reactions. So, this is what is my interest, but then I am calculating other 8 also in this formulation. So, need to calculate even the reactions for inverse dynamics, even though they are not my of interest at this stage, but actually for design purposes they may be useful, but not for this purpose of calculating tau 1 in my inverse dynamics. So, this is the formulation which you already know from your earlier knowledge of mechanisms course. Now, let us start from there. So, I do not want to calculate all those reactions, I wanted to avoid it, but at the same time now I wanted to get this tau 1. So, let us see now what I did, instead of putting all them together, let me put 3 links, the first 3 links, one link, second link and 3 link coupled by those joints. So, that means after dismantling it, I am mantling it again, but except the last joint, because I wanted to create a serial joint and I have good knowledge of serial system. So, can I apply my serial system formulation? So, 3 join first 3 links to form the 3 link system, but then I know that there is a reaction here. So, I keep it this reaction as it is. My intention is, can I treat this F03 as an external force acting on this 3 link system for which I know the formulation. Okay. Only challenge will be this F03 in case of typical 3 link system, somebody might be giving it as an external force right here, but here this is a reaction coming from the joint. So, I have to find out a way how to calculate that also. So, let us go back to our serial system formulation. In serial system formulation, I have told you that m t dot plus w m t is equal to w e plus w c. That means, all the external forces and moments applied on it and all the constant forces and moments acting on it. Okay. Constant forces moments in this case is these forces. If you treat it as a 3 dimensional object, okay, so then the reaction moments on the other direction will come. So, to make a uniform development, for the time being, let us treat all of them as a special motions, and my dynamic constraints will take care of all these constraints to bring it to the final equation of motion. What we have learned in our serial chain system, that N D transpose N L transpose, if you pre multiply, you will get the final equation of motion. But now, my equation of motion will look like, it is a 3 link system. So, I theta double dot plus C theta dot equal to tau E, which is the external actuating torques, plus tau C. Let us go to the paper to explain this aspect little detail. So, I have m t dot plus w m t is equal to w e plus w c. So, for a 3 link system, I know this will be 6 n, that means 18 by 18 matrix and so on and so forth. We have seen in our serial system that if I pre multiply N T transpose N L transpose, if I pre multiply N D transpose N L transpose, for open loop open chain system N D transpose N L transpose W C is equal to 0. Okay. But here I have F03 at the end. Okay. So, for present cut open system N D transpose N L transpose W C is not 0. Okay. Now, I would like to show that aspect, that how this is not 0. If it is not 0, what is the result coming into actually. Okay. So, this aspect I will do it little slowly. So, that is the reason that tau C has come into picture, that means the torque due to the constraint, and here the constraint means F03. Other constraint actually will make it 0, but this guy F03 will not make it 0. Then what is this tau C? Tau C is nothing but J transpose F03. What is J? J is nothing but the Jacobian of this 3 link manipulator. Okay. That is the derivation I will show you, that this J basically is the velocity portion of the Jacobian, because in this case rotational motion is not constrained, only the linear motion is constrained. And generally we find that thing from the loop closure equation, that A0 is this vector here, A0 plus A1 plus A2 plus A3 is equal to 0. And then if you do the time derivative of those, A0 dot is nothing but 0, because it is a fixed link, A1 dot plus A2 dot plus A3 dot is equal to 0, and if you rearrange, okay, then this Jacobian J will come into picture, and its dimension for the planar case will be 2 by 3. So, when you multiply with J transpose here, it will be 3 by 2, this is already 2 by 1. So, finally, it will be 3 dimensional quantity. So, this is already 3 dimensional quantity, and of course, this is also 3 dimensional quantity. So, consistency is maintained. So, left hand side we know from our serial chain analysis. So, we will not bother about the left hand side at all. Right hand side tau e and tau c, tau e consisting of the vector of external torques. If you go to the serial chain system, then bringing the analogy. So, here we have only the external torque applied is tau 1, no external torque here, no external torque here. Okay. So, which means this tau e will have tau 1 0 0 elements, and then tau c is our interest to see what is this expression. So, that proof I wanted to show you now, that tau c is nothing but J transpose F 03. Okay. And these derivations which I will show you in 2-3 slides, next 2-3 slides, will also help you to understand the analysis which in some cases I have not derived in detail. For example, in my serial chain system I have done it only single link and double link, but here I need to do it for 3 links. So, derivations will be much clearer from these equations. Okay. So, for 3 links, so twist of the first body, twist of the second body and twist of the third body I write here as a 18 by 1 vector, and it consists of NL, ND, NL, ND and theta dot. Theta dot consists of the joint rates of the first joint, second joint and third joint. So, first joint, second joint and the third joint here. And this is the structure which we have seen it earlier, and now I want to calculate NL transpose W c first. So, NL transpose W c first here. So, this and this, after that I will do N T transpose. So, I write it here NL transpose W c. So, 1 is 1, B 2 1 transpose goes here, B 3 1 transpose goes there and B 3 2 transpose there and 1, and I write them as W 1 c, W 2 c, W 3 c. Okay. Then I start from the last element, because it is multiplied with the identity matrix. So, this remained as a W 3 c, no problem. This guy here becomes W 2 c plus B 3 2 transpose W 3 c. Okay. I have given it a name because of a purpose. Let us see what is the purpose. Then the first column row will be multiplied with this column vector. So, identity means W 1 c here, this is B 2 1 transpose B 2 1 transpose W 2 c, B 3 1 transpose W 3 c, but I have written is B 3 transpose and 2 1 I have taken it out. That is because now there is a property of B 3 2 B 2 1 is equal to B 3 1. Let me show you on this paper how this is true. Suppose I have now the 3 link system. So, I have this is C 1, C 2 and C 3, and B 2 1 by definition it is 1 C 2 1 cross 1 0 1. What is C 2 1? C 2 1 is actually this vector. Okay. Then B 3 2 is equal to 1 C 3 2 cross 1 0 1. 3 2 is which vector? This vector. Okay. And then B 3 1 is equal to 1 C 3 1 cross 1 0 1, and what is C 3 1? I will put it in the red. C 3 1 is this vector, and if I multiply B 3 2 and B 2 1, B 3 2 and B 3 2 1. So, you have 1 C 3 2 cross 1 0 1 and then I have 1 C 2 1 cross 1 0 1. So, if you look into it, so identity then this is C 3 2 cross 1 plus C 2 1 cross 1 0 1. So, this can be written as C 3 2 plus C 2 1 cross 1 0 1. So, from our earlier diagram, C 3 2 is this much and C 2 1 is this much. What is the total? C 3 1. So, now I can write it as a C 3 1. So, now this takes the shape of 1 C 3 1 cross 1 0 1, that is equal to B 3 1. Okay. So, that is the property I have used on my slides to write the top expressions here. And what is the advantage I get it here? What is the term within the bracket? Please note that this term in the bracket here is nothing but the term I have calculated in my previous step here, which I have denoted as W 2 tilde C. So, that is again one of the point I wanted to mention, the recursiveness, that how recursiveness is coming. So, here is one recursiveness. So, I calculated W 3 C, I multiplied by P 3 2 transpose and added W 2 C, I get one term and then that term I multiplied B 2 1 transpose and W 1 C added. So, recursive. Okay. Okay. So, proceed next. Now, here I have indicated what is B 3 2 transpose. So, B 3 2 transpose is 1 and then when I take this transpose, I need to show these transpose expressions on the paper. Suppose B 3 2 is 1 C 3 2 cross 1 0 1 and B 3 2 transpose is actually 1 C 3 2 cross 1 transpose 0 1. Now, if I have not mentioned earlier, C 3 2 cross 1 is actually a skew symmetric matrix and this will have a term 0 0 0 and then you know what is the meaning of skew symmetric. So, suppose this will be C 3 2 x minus C 3 2 x, C 3 2 y minus C 3 2 y, this will be C 3 2 z minus C 3 2 z, like this. So, transpose of a skew symmetric matrix is what? The minus, and as per our diagram, so C 3 2 is this vector. So, minus of C 3 vector is what? So, which will be this one, so which is C 2 3. Okay. So, now I can write this as a 1 C 2 3 cross 1 0 1. So, all these things, that is one of the point I was mentioning in my earlier classes, that do not use the computer at the early stage, no, so that I can take advantage of this kind of geometry and the algebraic properties. Okay. So, that is B 3 2 transpose, which I have indicated here, and now I would like to go down to see what is W 3 C. Now, W 3 C, I have this free body diagram indicated on the top. So, n 0 3, as I told you, let us treat it as a general spatial motion. So, there will be n 0 3, obviously n 0 3 means about z axis there is no reaction obviously, because it is allowed to move, but about x and y there will be some component. So, that is why n 0 3 comes, n 2 3 comes, and then because of those reactions from the two edges I have this cross product terms, now minus d 3 cross f 2 3 plus r 3 cross f 0 3. And this is my moment components for the definition of range, and these are my the force component. Okay. So, what is W 2 C? Okay. I am going little slow here for better understanding. So, W 2 C tilde is this much. So, B32 transpose W3C plus W2C, if you do this operation, okay, so this part is nothing but W2C component and this part the below is B32 transpose W3C.